Okay, I wanted to give you a bit of feedback about the developing tail recursive functions, and I thought I'd do that by doing a bit of live coding. So here we go. Let's take a look. In the window here, we've got an editor, and let's start off by defining our Fibonacci function. Let's think what our function is going to do. Well, when we've counted down to the base case, we've got the previous value and the current value in our two accumulating parameters. So what we're going to do is output the previous value. What do we do in the general case? Well, we're not at the end of the loop. So when we've got the previous and current value here, what we do is we do a recursive call, counting down by 1, but now the current value becomes the new previous, and the previous plus current becomes the new current. So that gives us our definition of Fibonacci function. And we'll export that so that we have our 3-argument Fibonacci function. Now actually, how do we start it? Well, we need to start off. If we want to calculate the Fibonacci number for n, we'd better take our Fibonacci, start it at n, and the starting values are 0 and 1. Now you can see we've got a little red line there. That's because fib1 is unused. So I'm getting a sneak preview of what the compiler will say here. I've got rid of that. And in fact, we're getting the warning here because C is unused, so let's put an underscore in front of it. Now if we save that and compile our function, we should get what we want. And in fact we can test it out. I have tried it already. Fib0 is 0, fib1 and fib3 is 2, fib4 is 3, fib5, fib6 is going to be 8, and so on. So we've got it, it's doing what we wanted. So there the two variables in these two positions are taking the role of the previous and current values of Fibonacci, and we as we go count one step down, we iterate one step forward in that way. Now we could, if we wanted to make this a bit more direct, we could do a 4-argument fib where we counted up from 0 to n, but I suppose I've just omitted that argument here. What about checking for a perfect number? What do we need for a perfect number? Remember, a perfect number is a number which is a sum of its own divisors. So what we're going to have to do here is when we have found that, suppose n is the number we're looking at, and we've counted up to n, and we've got the sum of divisors to be s. Now, what does it mean for a number to be perfect? N has to be equal to s. So we have, that's our base case. What about when we have a number? We've only counted up to m. Our current number is m, and our sum so far is s. When are we going to, and what we're doing in s is adding the divisors. Now when is m a divisor of n? That is the case when n rem m is equal to 0. Okay. The remainder on dividing n by m is 0. That means s is a divisor. Our tail recursive call is n plus 1. So we check the next number, and we add m to s. And then our final case is when n, m and s is not the case. What we do is we don't add anything to, we don't add anything to the sum, but we just call it with s. And then our top level check is by initializing our 3-argument function with n, we start counting at 1, and we start our sum as 0. So the second argument there is the current number we're looking at as a potential divisor, and the final argument is our sum so far. And let's export perfect. Let's save that definition. Let's compile tail, and then let's call tail of perfect of 6. True, what about 28? True, what about 29? False. Okay. So that looks as though, on a very small test set, that looks as though it's giving us the answer we wanted. And again, what you can see here, looking at the definition of perfect, it's a loop. We have 2, and what we do is m gets incremented by 1, s by m, or nothing, depending on whether or not that case holds. So there we are. We've seen Taylor recursion gives us this looping behavior. We've also seen in the previous video that it can also do, we can do side effects during that loop if we want to, for example, printing out numbers. So it is a looping construct. But remember, we still don't have any assignment in here. All we're doing is changing the values of these arguments. We are not assigning to mutable variables. All our data, all our variables, all our naming is immutable. Okay, that's it for this quick recap on Taylor recursion.